All right, so we are now looking at the third aspect of this course, which is concurrent programming. And concurrent programming is hard. We sort of like to think sequentially the way we are programmed from the very beginning. We like to think of events happening one after the other. It makes it easy for us to think about the possible outcomes of a program. It's easy to debug sequential programs. There is a clear notion of time. Time advances forward, and there is one flow of instructions. And when we move to concurrent programming, as we saw with processes and signal handlers, possibly executing at the same time concurrently, there's a lot of possible interleavings, ordering of events that we have to think about. And we have to care about the integrity of the data structures. So if the process is manipulating a data structure and a signal handler starts running, we now have to care about, that a specific structure array is going to be accessed from two different flows in the execution. So there are some well-known problems with concurrent programs. We already saw races when we were looking at processes where the child process or the parent process could potentially do something which is not in our control. It depends on scheduling decisions made by the kernel, or the signal handler could do something first, and the parent process won't have the opportunity to do some bookkeeping before that. So races are very common in concurrent programs. An example is, in reservation systems, who gets the last seat on an airplane? This is not very deterministic or very easy to reason about. It depends on multiple events potentially happening almost at the same time. So we will look at, in the next 3 or 4 lectures, how to write programs where we deal with these conditions, where there are potential races. Then there are deadlocks. So imagine the main program acquiring a lock on a data structure, and then the signal handler starts running at some point, and it needs the same lock on the same data structure to make progress. And now the signal handler cannot make progress, the main program cannot make progress, and we have a deadlock. In real life, imagine a 4-way intersection where whoever gets first has the right of passage, and if 4 drivers arrive at the same time, then it's who came first and who can make progress. So this is an example of deadlock. There are fairness issues. If there are multiple flows, once again, a sequence of instructions with a program counter that increments by 1 each time. And there could be multiple flows that are scheduled on a CPU, and somehow the kernel does the scheduling and make it all appear as if, make it appear to each process as having a separate logical flow. And fairness is also important because if one process or one logical flow is running all the time, then other processes or flows won't have the opportunity to make progress. Starvation is similar, where some process won't have the resource that it's looking for. And the way we write programs, concurrent programs, we have to make sure there is fairness, there is no starvation. Live logs, a real life example of live log is when two persons, encounter each other in a corridor and they both go on the side and no one, so they are doing something, but no one is getting out of the way of the other one and they cannot make any progress, even though they are spending some energy trying to do some work. So we won't be covering all aspects of concurrent programming here. Some of them. It's a very broad topic with a very rich history. And we want to continue looking at concurrent programming from the perspective of iterative server. Because if we don't write concurrent servers, then these are not, they won't work properly. And we will see today problems with our sequential server and how to make it concurrent in a number of ways. So iterative server that we've been looking at processes one request at a time. So let's do this. So what's the problem with this server that we looked at in the last few lectures? So imagine we have two clients that want to connect to the server and they want to play echo. They want to echo a message. They want to send the server a message and they want to receive the same message back. This is an echo client server. So client one here tries to make a connection which is accepted by the server. So let's focus on this transaction first here. Then the server blocks in the read. The server blocks in accept initially, and then connect. Client one makes a phone call. Server picks up the phone. It was blocked in accept, waiting for a phone call. It picks up the phone, and then it blocks again in read. It blocks in read because unless the other party says something, the server cannot make things up, right? It has to block in a read. The client writes something. This is equivalent to now sending a message. This is equivalent to now there's a conversation going on. The client says something, and the server can now get out of the read and send the same thing back. And this is the echo that this application does. So the server writes something, and then the server, it's an iterative loop. It's an iterative while loop, if you recall, and the server blocks in read again. You want to say something else? The server is now all ears and waiting for the client to say something. The client closes the connection, which sends an end of file. And this is a condition that is detected by the server, and it closes the connection, okay? So this is a transaction that took place between client one and server, okay? So this is a sequential server, once again, and unless the client one closes the connection, the server cannot do anything else except having a conversation with client one. Now, while this transaction was taking place, while client one and server were having a conversation, client two tried to make a connection request. Now, unfortunately, the way we written our server, the server is hooked up to client one, and it cannot accept this request. This is when you're talking on the phone and someone tries to call you, you cannot attend to two clients at the same time. The client two here sends a message using the write function. The server cannot respond. Client 2 then blocks in read. This is the echo client server application. Now the client wants to hear back what they said, what they sent to the, this is a send to the server. Only when the server is done with client 1, right here, when the server is done with client 1, it accepts, it goes into accept again. So when it is done with client 1, it closes the connection and goes back to accept to talk to someone else. And they realize, oh, there is another client that wants to connect. So this connection now succeeds, and then the read-write transaction takes place. And this is why this is a sequential server. It can only interact or have a conversation with one client at a time. And all this time, the client 2 is waiting for the server to finish with client 1, right? This server works, but this is not what we want from our servers. We want our servers to be concurrent, to be able to serve multiple clients at the same time. And this is how transactions take place on the web. If the web servers were sequential, then we would be stuck all the time because someone else will be using the service while we request the service. Now, the important thing here is to figure out, and this will inform the design of the concurrent server, where does the second client actually blocks? So where does the second client blocks? The call to connect actually returns successful. So here, when this transaction is taking place between client 1 and the server, disconnect, client 2 does not block after this connect function. It simply returns. And the reason is, even though the connection is not accepted, the server-side TCP manager queues the request. So we know by now that inside our operating system's kernels, there's a lot of buffering. The operating system's kernel, which is running the TCP manager, actually has this mechanism to buffer incoming requests. And this is sort of an optimization in the kernel. It's buffering all the, it's like when you're talking on the phone, something in your phone is taking a note of all the other people who are trying to call you. So when you're done with the phone call, you can see who called me while I was talking on the phone. So this is the same functionality that the TCP manager provides. And this feature is called TCP listen backlog. So TCP is a protocol somewhere in the hierarchy, in the protocol stack, that one of the services it provides is to create a backlog of clients who were trying to talk to the server while the server was busy doing something else. So this is an example of, there are some things in our systems that happen in the user layer, okay? The way we write, when we write applications, there are few things that we have to take care of. And there are few services that the kernel provides. And this division of who does what is very important when we write software. So this is an example of the kernel creating a backlog, doing what it can. Now the kernel cannot make up things on behalf of the server. This is something that the application writer has to do. The server cannot start interacting with the client, assuming the client wants, kernel has no knowledge what kind of service the client is looking for, right? So this division of labor, what does the operating system do and what does the application do, is very important. So here, the server-side TCP manager, the server-side kernel, is queuing up requests for connections. The call to write also returns. When the client 2 is trying to send a message, the client 2 doesn't have to block. Why should the client 2 block? It simply wants to send a message, and it will send the message. It's a write. All the data that is needed to perform the write operation is available on the client side. It will just send the message. You know, this is like leaving a message for the other party. Hey, when you are done with whoever you're talking to, I have this message for you. And the server-side TCP manager buffers up this data. Now the client 2 actually blocks in the read function, whatever this function is, read line B, that I told you to look at. Because now the client 2 wants to hear back what it just sent. And there is no way for client 2 to make progress at this point unless the server accepts the message and echoes it back. So what we have learned from these 2 slides is that on the client side, the connect function will return successfully. And so the scenario is that there's a conversation taking place between server and client 1. They're playing echo. Client 2 tries to make a connection, which I'm saying returns. So client 2 will make progress, write will return. So these all will be buffered here. The request for connection, the write data, all this will be buffered in the server, somewhere in the server's.
How much thing time to write for the TCP waiting?
Right. So this depends on certain settings, certain variables. When you install an operating system, there are defaults, but then you can override the defaults. There is a limit. And if you're not careful, a malicious client, a client with not a goodwill, can actually exploit this. You know, it can actually write so much for you that no other client, it can fill the buffer. So there are certain constraints, how to deal with these situations. Per client, there is a maximum buffer size, things like that. Those are all part of the configuration parameters. That's why operating systems, if you look at, there's a lot of parameters that you have to set. And those buffers, your observation is correct. Those buffers have a limit. You cannot just send unlimited information. Right. So then the server side will just start dropping things. It's just an optimization, right? I mean, the kernel is providing this feature. It doesn't have to. Right. Things like that. And this read on the client side will actually block, because reads are kind of, when you want to receive something, read is like a receive. When you want to receive something, you cannot make up things. Someone has to send something. All right. So we know that how the sequential server is actually working. This gives you more insight into sequential servers. Now, what is the thing that we actually want to fix? Why do we want concurrent servers? So imagine that client 1 is hooked up to the server playing echo. So they start this transaction, and at some point, client 1 goes out for lunch and is never seen again. I don't know, they jumped from a window or something, whatever. They never return to the desk. So we don't care about the user in this course, but we want to see what's happening on the server side. The user is gone. Now the server is blocked in a read, waiting for data to arrive from the client one, but client one is, let's say, dead. So, and client two is blocked in read as well. So how should we fix this? So this is a fundamental problem with sequential servers. This is not how the World Wide Web can work. That's why I was saying that this server is correct. I mean, there are no errors in its execution, but it's not written properly. We want to fix this scenario. There won't be any progress here if there are a number of clients waiting for the server who are still alive and who have good intentions to interact with the server. They are now all, they cannot make any progress. They're all blocked in this read function, waiting for, and you can imagine other problems. Things are buffering up on the server side, TCP manager, new connections are arriving, new structures are being created in the server's memory, and nothing could happen. So this is not how we want to write server-side applications. So we need concurrent servers that use multiple concurrent flows to serve multiple clients at the same time. Concurrent flow is where you have a sequence of instructions on one side, another sequence of instructions. There's a program counter associated with each of them. Let's say this is the flow of client one, this is the flow of client two, and they both are scheduled on the same CPU, and somehow the kernel makes sure that both flows actually make progress and they don't observe that the other flow is also scheduled on the same CPU. And we talked about this when we looked at the process abstraction. So there are three ways to write concurrent server. Process-based is where you have a separate process for each client, and server creates or forks a child process to deal with each client. And so if one client is, disappears, then other clients are not impacted by that. And in this case, we say that the kernel automatically interleaves multiple logical flows. All the application has to do is to use fork and properly read the child processes. In this case, each flow has its own private address space. So because for each child, for each client, we are creating a separate, we are forking a process, a child process. Each client will have its own private address space, which may be a bit of an overkill. So this is a heavyweight way to create a concurrent server. An event-based server is where, so writing a process-based server is really easy. You just fork a child each time there's a connection request, and then the kernel will take care of how the interleavings take place and who is scheduled when, all those things. In an event-driven server or an event-based server, the programmer takes control of creating these interleavings, how to schedule the multiple flows corresponding to each client. And all the clients or all the flows share the same address space. So we have one process, and somehow the way the programmer writes the application, they are able to do some work for each client based on an event. Whenever something arrives on a specific file descriptor, the programmer does a little bit of the work. And this technique is called I/O multiplexing. You have multiple input-output operations on different file descriptors that belong to different clients, and the programmer is going through this this array and checking which descriptor has an input event, okay? And all the descriptors that have some bytes available for reading, the server does take some action, okay? There's one process, and it's complicated. We'll look at the code in a little bit. It's complicated to write event-based servers, event-driven programs. There is only one address space. There is one address space, because we are not forking a new child for each client. So there's one address space, and there is one sort of right, and they all share the address space. And then thread-based servers. So the plus side of this is that the kernel performs the scheduling. And scheduling refers to how you interleave the multiple logical flows onto a single CPU. The plus side of event-based is there is a single address space. There is one address space, low overhead, multiple clients can share data because it's one address space. Remember that when you have an address space, there are overheads. The kernel has certain data structures, VM structs, certain things. Address spaces are not free. It takes up some memory. So thread-based servers combine the advantages of both these approaches. The kernel automatically interleaves the flows, and we'll see how the kernel does that by giving us a new abstraction similar to a process, but lightweight, that is called a thread. Process is very heavyweight, as an entire address space, code, data, heap, blah, blah, blah. And switching between two processes is a very heavyweight process, very complicated. So the kernel gives us the abstraction of threads, which are lightweight, and all the threads share the same address space. And this is a hybrid of process-based and event-based approaches. Now we want to understand deeply all three of them. And okay, so let's start with the process-based servers. Probably the easiest to understand. So the key idea is to spawn a separate process for each client. So here, when client one tries to make a connection with the server, instead of previously it would, after accept, it would execute the read function and block in it. Now it is just going to fork a new child. And that child will handle client one. So, and for client two, it's going to fork another process. So after forking the child for client one, it's going to get back into the while loop, going to go back and accept a new connection and fork a child for the client number two. So this is a fork for client number two. And then this way, we have two logical flows for two clients. And if one client disappears, it's not a problem for the second client. The client number two can still make progress because it's a separate process, okay, running concurrently. And its scheduling, it's how it runs on the CPU is all managed by the kernel. Okay, we don't have to worry about it. So this is the while one loop that we have been looking at for a while. So this is the data structure to store the client address, and this is a variable that makes sure that the client length we have enough space, storage space for the client, regardless of if it's an IP4 or IP6 client. So in accept, so while we accept, the server blocks in accept. This is a listening descriptor that we open here. So there's one listening descriptor during the lifetime of the server while the server is running, and there are multiple connected descriptors, one corresponding to each client. So the client, the server, so this is where the client address, when a connection succeeds between a client and the server, this is where the client address information is stored. And what we get from accept is a connected file descriptor. So instead of calling echo, as we were doing before in the sequential server, here, the server is forking a child. And the child executes echo. So echo now runs in the context of the child. And the next thing the parent does, so this is fork equals 0. Recall that fork returns 0 to the child and the process ID of the child to the parent. So only the child will execute this code. Parent will execute this line and then go back to accepting a new connection. Now the parent is closing the file descriptor, the connected file descriptor, because the parent doesn't need the connected file descriptor. It's the child that needs the connected file descriptor because the child will have a conversation with the server. Similarly, the child doesn't need the listening file descriptor. And closing these descriptors is important because the kernel keeps a reference count of how many processes are using a descriptor. And only when the reference count is 0, does it free all the data structures associated with a specific file descriptor, specific connection. And child inherits all the file descriptors of parent. So it's important for the child to close the listen file descriptor. Actually, when a process exits, all the file descriptors close automatically. So this is just for avoiding good practice. But for the parent to close this descriptor is important. If the parent does not close the connected file descriptor, which it does not need, it's the child that needs the connected file descriptor, because after forking, the conversation will take place between the child and the server. The parent will just go back in the while loop to accept a new connection. So for the parent, it's important to close the connected file descriptor. And then to properly reap all the child processes that the parent will create, we'll use the wait PID from week 4. Okay, that's really simple. It's really simple. And now we have a concurrent server. We have a concurrent server. So multiple clients can play echo at the same time. And if one of them disappears, then the other clients can still play. Okay. So the way it happens is, assume that we have a client and we have a server that blocks in accept, waiting for a connection request on the listening descriptor 3. Let's say we have a listening descriptor 3 because 0, 1, 2 are taken by standard input, standard output, standard error by default for each process. So we have a listening descriptor 3, and then the client makes a connection request to the server. All right, using connect. What happens is that the server creates a child process that inherits the connected file descriptor, and the server goes back to listening for other clients. And the child process, now this phone call, this conversation, this connection is actually established between the client and the server child, not between client and the server, because the server has closed the connected file descriptor. The child has closed the listening file descriptor. So this is how it works. And if another client comes along, it will be able to connect with the server with the same mechanism, forking and closing the appropriate descriptor on both sides. Sorry, on the server side. So it's a really clean way to write a concurrent server. Connection requests, the parent process on the server side is listening for connection requests, and the clients are communicating with the server process using forked children. There's no shared state between multiple processes that are serving multiple clients, because each process has a separate private address space. Both parent and child have copies of listening and connected file descriptor. The parent must close the connected file descriptor. This is important once again. The parent must close the connected file descriptor, otherwise we have a memory leak. And the child should close the listening file descriptor. When the child process terminates, the listening file descriptor will close automatically, but it's a good practice for the child to close the listening file descriptor. So the listening server process has to reap zombie children. The parent process must close its copy of the connected file descriptor. We discussed all that, and the reason is I told you that the kernel keeps a reference count for each socket, how many processes have that socket open, and the connection will not be closed, and the data structures will not be reclaimed inside the kernel unless all the processes close the file descriptor. And we call it reference count. When the reference count is 0, we do. So the advantage of process-based server is it can handle multiple connections concurrently. It's a clean sharing model. Descriptors are not shared. Global variables are not shared. Some data structures that are used to provide the file abstraction are shared. Those data structures are on a per file basis. So file tables and some other things are shared, but that's typically not a problem. It's simple and straightforward. So for each socket, there are certain data structures that the kernel has, file table, some other data structures that we looked at in the storage lectures. Those data structures are indeed shared, but so there's a lot of overhead for process control. Processes are very heavy. They have an entire address space associated with them, page tables, a lot of things. And it's not easy to share data between processes. Because each process has a separate address space, if you want to share data, it's very hard. And there are mechanisms that we won't look at in this lecture, in this course, pipes and other things for inter-process communication. But for many applications, it becomes a problem. If clients want to somehow share information, that is common. Okay, event-based servers. What happens here is that server maintains a set of active connections. It's an array of connected file descriptors. Let's say -1, -1, -1. So there are some descriptors in the array that are active, and there are others that are simply not available yet. So the server then runs this loop. For the descriptors that have pending input, there's a special function that the kernel provides called select. There's also epoll, but we will use select here. And you can ask the user program, the application can ask the kernel, here is a list of file descriptors. If there is input on any of these descriptors, wake me up, let me know. So after calling the select function, the application, the user program, the application suspends its execution, okay? And whenever there is input on any of these file descriptors, when there is at least one byte to read, the kernel will wake up the application and will give it a list of file descriptors that have some input on available, okay? And then the application can go over the array and take an action for each of the file descriptor. So this is, I'm just showing the connected file descriptors. Usually, well, at least in our example, almost always, we also include the listening file descriptor in the array that we pass to the kernel. So let's say 3, 4, 5, whatever. So we ask the kernel using select function, hey, if there is input, if there is an activity on any of these file descriptors, tell us, wake us up. And then when the program, when the application wakes up, it is blocked in select. When it wakes up, it checks to see what the kernel has, which descriptor, according to the kernel, has some activity on them. If the listening file descriptor has input, then the corresponding action is to accept the connection. There is a new connection being made by a new client, and add the new connected file descriptor to the array. Otherwise, service all the connected file descriptors with pending inputs. So this is more like an event-based system where you go over all the possible clients and check for events, and then take an action corresponding for that is appropriate for each client. Okay, so imagine we have active descriptors here. So these are all the active descriptors. So we have the listening file descriptor, and we have a bunch of connected file descriptors in red. Some of them are inactive, okay? And then after select, the green ones, according to the kernel, are the ones which have some input available. And so we can service this one by adding this new client to the array. We can service these by echoing back the message that the client sends us, okay? So this is more like so the kernel is basically informing us that there is a change in the state of the corresponding file descriptor. Previously, there was nothing on this file descriptor. Now there is some input. So take some action. So we are responding to changes in the state of each file descriptor. And this is sometimes called, writing a state machine. So there's one logical control flow and address space. It is still easy to debug. Process-based servers are hard to debug because you have to, the debugger has to do some bookkeeping for each concurrent child, which is hard. This is still one logical control flow. You are going over events and doing things sequentially. So this is more like mimicking concurrency using event-driven programming. So there's no process or thread control overhead, and a lot of systems, JavaScript, Node.js, others use this model. As we will see soon, it's very complex to code compared to process or thread-based designs. It's hard to provide fine-grained concurrency. So basically, you want to go over the event list and do something very quickly for each client. And one client can do certain things by not providing enough information for you to process the request, and it can make the server execution very inefficient. And event-based servers cannot take advantage of multi-core. When you fork a separate child process in a process-based server, each of the child processes can run on a separate CPU core in today's multi-core processors. So multi-core processors have multiple CPUs, and each CPU can run a separate process. And this is an example of parallelism in today's processors. This is just one process. So there is no parallelism. Even if you have multiple cores, this is just one process. So the operating system cannot do anything to take advantage of multiple cores. It's just running on one CPU. And that's a problem with JavaScript and other similar event-based systems. Okay, so I want to do some demos before I move on to the third to make this discussion more concrete. How should we do that? All right, so let me. All right, so let's start with the process-based server. Now, this is hard to see in shell that indeed there are two. Each client is being handled by a separate process because we're just not doing enough work in Echo. But let's see. So this is our code where we are forking a child and doing everything. So let me start this server on port 9000, and let me start the client. So let me connect the client to the server. So what we want to say is, if multiple clients are able to talk to the server without one, and they will both keep their connections open. They will not close their connections. So we have two clients that are connected to the server. And if one client says, so there's echo, the server received 13 bytes. So I'm not closing this connection now. And the second client, and so with a sequential server, once a connection is established between one client and the server, that connection has to close before the server can respond to another client. But that's not the case here. I can have as many clients as I want, and they all will be able to play echo at the same time. So this was the sequential server. So if I do this, get it back. So the second client, so this is the sequential server. The second client comes in and there is no echo because the server is hooked up to the client that came first. All right, that connected first. So if I close this connection now the server goes back in the while loop and echoes to the second client. So remember this distinction, which is very important for your assignment and for the next labs, because we are going to move from sequential servers to concurrent servers. So we can clearly see that sequential server is hooked up to one client and cannot do anything else in the world. It's just focusing on that one client. Only when the client closes the connection, which sends an end of file condition to the server, does the server goes back into the while loop, accepts the next connection, and echoes back. And the message that was sent by client number 2, even though nothing was echoed back, client number 2 the message was not lost. It was buffered on the server side TCP manager. So here, when I wrote to this message, this was not lost. And the server accepted the connection request after it came back from serving client number 1. Okay, and we saw that the process-based server does not have this problem. We had two clients that were communicating at the same time. Okay, so I want to show you an example of the select function that I talked about. So what we are going to do here is this is a program that lets us respond to standard input and connection requests from a client at the same time. So let's go through this. So there is a data structure that is provided by the kernel file descriptor set, FD set, which is just, and you can think of it as a bit vector. So it's a bit vector, it has a certain size, and we can set bits in this descriptor set to give the kernel some information corresponding to that index in the bit vector, and to receive some information from the kernel about that descriptor. So we have two file descriptor sets, read set and ready set. So what we are doing here is, so first of all, we create a listening descriptor. So this is a server, sort of a server. This is a server that will also listen to keyboard input, standard input. So we open a listening descriptor. So we use these macros to initialize the read set to all zeros. So all the bits are cleared. And then what we are doing is we are setting 2 bits inside this bit vector read set. We are setting the bit corresponding to the standard input file descriptor, which is always 0 or 1 something. That's the constant we use for convenience. So we are setting the standard input file descriptor. We are adding it to the read set. So we're adding the standard input to read set because we want to ask the kernel, hey, soon we will ask the kernel, hey, I'm going to sleep. I'm going to suspend myself. If something happens on the keyboard, on the standard input, let me know. Not just that, we are also adding the listening file descriptor to the read set. So we are adding 2 file descriptors to the read set because we want to ask the kernel, hey, I want to suspend myself in a little bit because I'm trying to write an event-driven application. If something happens on either of these 2 descriptors, let me know, okay? So what happens next is we have a ready set. We have a second file descriptor set called the ready set because so read set will not change at this point. These are the 2 descriptors that we are interested in for the entirety of this application. Okay, we are interested in the standard input and the listening file descriptor. So we set the ready set to read set, and we provide the kernel with, we call a select function, and we give the function a pointer to the ready set. And here the first argument is the cardinality of the ready set. We are telling the kernel there are about 4 file descriptors in the ready set, 0, 1, 2, and the listening file descriptor. Okay, so 0, 1, 2 are created by default, and then listen file descriptor is something we created, this program created. So there are 4 file descriptors at this point. Because it starts from 0, we have to add 1. So we're telling the kernel, hey, here's a ready set, okay? It's a bit vector, certain bits are set. Take a look at those bits, and if there's any activity on those file descriptors corresponding to those indices in the bit vector, wake me up.
So if it's running like a non-POSIX system where there were more than 3 starting file descriptors, or something like where you're looking at these and file descriptor, this wouldn't quite work.
But there will be another way to get around that, right? Yeah. So listen FD will always be the next one, right?
Yeah, what if you don't include all the previous ones? Because like you didn't include standard error.
Because I don't want, that's a descriptor that is used for standard for display, right? I'm not in.
Are you getting the number of file descriptors just by getting the N1 and adding 1 to it?
Right.
So then, if you didn't include standard input, I don't think the exact number, but like the range of the like, so it's like not the number of ones or the like bit vector, but like how much of it we want to do. Oh.
It's how many are there in the, and some of them are set So select, the first argument is how many descriptors are of interest. So we have to include, because we want to include standard input, we have to include all 4, but we can set those bit vectors, those bits in the vector to 0 where we are not interested. So we are only, so there's only a few operations you can do on the file descriptor set. You can, and they're all here. You can set it to something, you can set a specific bit in the vector, you can clear it, you can do an assignment, but that's about it. And there's one more, we'll see soon, but that's about it. There's nothing much you do with the file descriptor sets. And these are the only macros we use. Now we suspend our execution by calling select. And this ready set, we gave the kernel a pointer to ready set. The kernel is going to write something to this ready set. So when we return from select, we cannot assume that we can reuse ready set because the state of bits in ready set are going to change. So what the kernel is going to return is a ready set with certain bits that would be 1, and those bits will tell us, the 1 bits will tell us that there is some activity on those file descriptors. So we gave kernel the read set, which was like, I don't know if I can write here now, I don't think so, which was probably 1001, and the kernel might return to us 0001. So there is some activity on the standard input, but there is nothing happening on the listening file descriptor. And that's why we come back in this while loop, and when we return, we again assign the read set to the ready set. So read set is not changing. These are the only 2 descriptors we are interested in for the entirety of our program. But the kernel will play around with the ready set to give us some information about, some state has changed. Something has happened on one of the descriptors or both descriptors. So, and then in the if loop, we use the macro FD is set. So now we are checking if we return from the select, we were suspended, we were blocked in select. If we are now executing, then obviously the kernel has returned something. Something has happened on one of the file descriptors or both. So now we're checking if something has happened on the standard input. So here's a pointer to ready set, and we are checking if something has happened on the standard input. We do one thing, we execute this function command. And I don't know what that function does. We'll see in a little bit. On the other hand, if there is something, if the listen file descriptor is set, if FD is set, listen file descriptor is true, then we need to accept this connection and start playing echo. Okay.
In the select function, is ready set kind of acting as like an input and then output?
Yes. It's acting as an input and an output, right? And that's why we are doing this assignment here. So ready set in the select function is acting as an input and the output. So the kernel will read all the bits that are set initially to take a note that, okay, the user is interested in these file descriptors. And then it will clear all the bits and only set the ones. I don't know if this is the cleanest way to do it, but there's a lot of points in Linux where you can argue that, is this the cleanest way to do things?
I suppose like maybe nothing has been like frequency at like the end of like the body of the while loop. Is it possible to kind of return to the kernel? Saying like I don't want to loop again until later maybe.
So what we're doing here is we're going back to select, right?
So like, is there a way of like stopping it kind of like because it's like a while one loop? Is it possible to say kind of like wait until you do some other stuff before coming back to like looping back again?
Possibly, you can do that. So here you will be stuck in echo, by the way. So as we will see when we do the demo, if there is some activity on the listening file descriptor and you call echo, then you're just stuck in echo. Because until that client closes the connection, you won't come back to the while loop. So maybe it's already doing what you're saying. what I'm this is a powerful programming pattern, and a lot of today's application like JavaScript uses this model. So that's why I want to get into detail. Okay, so I think this is not very difficult. So if the file descriptor, listening file descriptor is set, if there is a state change, if the state of the listening file descriptor changes from nothing available to read to something available to read, then the program responds to that change in state by playing echo. So this is more like a state machine. We are programming a state machine. And the state is kept in the ready set, and whenever there is a change in the state, someone informs us, the kernel informs us there's a change in state, and we take some action, and we go back to the previous state, which is now it's empty. Tell me if there's something here. Okay, I guess what we should do is to see this in action to make it more concrete. So let's say select. So now the listening socket descriptor is 3. I'm not doing a printf. This is actually what I get. So 0 and 2 are taken by the standard input output error. The listening file descriptor is 3. So this is a server that is not listening on file descriptor 3. It has called select and is blocked. And it will respond to standard input or echo a message from the client. So the standard input file descriptor has also been added to the FD set. The file descriptor, the ready set. Let's see what happens. So what I'm going to do is, first I'm going to test the standard input. So let's say standard. All right. So if I press enter, something will happen on the standard input. So now it's saying command is writing on the screen whatever I wrote on the keyboard, and it goes back to select. So there was only one file descriptor on which there was some activity, the standard input. And so this select process program responded to that. Okay, what I'm going to do now is I'm going to open a connection. What happens when I do this is there will be some activity on the listening file descriptor, and we'll see what happens. So select will get out of the suspended mode and do something, and something will happen in the program. So if I open a client, nothing's happened, but I guess we need to play echo for something to happen. So let's say I say comp 2310. So now it's responding to the client. So server received 18 bytes. I haven't printed anything when I opened a connection, but maybe you can do that in the labs. Okay, what I want to show now is, so once echo is executing, the echo function is executing. Let's see if the select program is able to okay. No. Because in the while loop, we are stuck in echo. We haven't called select. Okay? We haven't called select. So echo is a until the client closes the connection, we will not return from the echo function. So we'll not go back in the while loop and call select. Okay, let's close the connection and see what happens. So let's close this connection. And now we see that calling select and blocking will respond to standard input or echo message from client. I guess it already did. So when I close the connection, I guess it already printed what I typed on the keyboard. Did anyone notice that? So let's do this again. So what we want to do is we want to open a connection, want to hook up the server playing echo. Okay, so now I'm typing keyboard, nothing happens. Let me close this connection. You see, the server, the select process, the program goes back to the while loop, and what happens? It calls select, and the kernel tells it there is some input waiting for you in this file descriptor, standard input. I haven't typed anything after closing the connection. When I close the connection, all this happened without me doing anything. I typed keyboard before I closed the connection, and I closed the connection. What happened? The program called select. The kernel said, hey, you have something waiting on standard input. The stuff that I typed before I closed the connection. And I did the fd is set and all of that. And the select program, it called command function automatically. This is the power of select, right? It's providing sort of buffering or this information about which file descriptor there was some activity. Okay. Okay, now you can see already that writing event-driven programs is more involved. So this is the code for the process-based concurrent server. What is that? I don't know, 40 lines of code, very simple, nice and clean. If you know how fork and reaping of zombie processes work, you can write it with your eyes closed. But if we go to the event-driven version, there's a lot of complexity here. And I'm going to go through this, but as with any code base that is a little bit more involved, we cannot go line by line, and some of that you'll need to do yourself. Okay. So first of all, we have a structure to for bookkeeping all the things that we need, the ready set, the read set, and we want to keep the list of connected file descriptors in a separate array. And if you read the code carefully, and if we get to that today, you will see that. Some of you might wonder if we have the read set and the ready set, and by the way, I leave it to you to Google and which header files you need to include to get FD set and all those things. You should be able to do this now. We don't have to tell you. Just Google FD set and they will sys types, sys, whatever. So there are some variables for bookkeeping: maximum file descriptor, number of ready file descriptors, maximum cardinality, the input buffers, and all that. Okay. So in the main loop, initially you initialize the pool. So this is a pool that is being initialized. As always, you open a listening file descriptor, and then in the while loop, you're saying the ready set equals read set select. This is pretty much the same. If there is activity on the listening file descriptor, what do we need to do? We have a new client. Very good. We're expanding our user base. We have a new client. So we want to add that client to our ready set. Okay, so if we go to the add client function, we will see that that would be happening. We are adding this new client with connected file descriptor to the ready set. And after doing that, the check client function, it's a for loop that goes over all the bits in the ready set, all the file descriptors, sorry, all the connected file descriptors. So that's why we have this distinction between, we have this explicit separate list of connected file descriptors, and we have the ready set and read set. The ready set and the read set, they include the listening file descriptor. Okay. The action we perform for the listening file descriptor is adding a client. The action we perform for the connected file descriptor is playing echo. Okay. So we want to keep the list separate. So if we go to check clients, we see that it's a for loop. Okay, there's a few checks and all that. I leave it to you. It's a for loop, and for each index in the for loop, we are getting the connected file descriptor from our list of file descriptors, and we are checking if the file descriptor, if FD is set is true for this connected file descriptor. If it is true, what are we doing? We are playing echo. Now, probably last question for you. What is different? What is the difference between the echo function implementation and this if statement? So we are going over the for loop, I equals 0 to the maximum number of connected file descriptors we have at this point, and we are, for each descriptor, if it is set, we are doing something. What is the difference between the way we are playing echo in this if loop and the way we are playing echo in the echo function that we've been using? So let me tell you what was happening. Remember when we started this lecture, we saw that what the server does, it accepts a connection, picks a phone, receives a message, receives a text message from the client, echoes it back, and then what does it do? It goes into a read, right? It goes into a blocking read to accept the next text message. And until the client closes the connection, we are hooked up. That was the flaw in our sequential server, that if the client goes away without closing the connection, the server is now hooked up to this one client. So in the echo function, we would receive a message, write it back, and then go to receive again into a blocking read. Here, this is not what is happening. So the way we have written this event-driven application is we read in line 112, we read something from the client. We are doing some bookkeeping, how many bytes we read in total up to this point. We echo it back at line 116, and that's it. We are not hooking ourselves to the one client. We are moving on. Okay, so we will move on with the for loop. And if there is another client with a line, with a text message on the file descriptor, we will echo it back. So we'll go over the loop, we'll check all the events that have taken place in that ready set, and for each of the clients, we will do something. We will not hook ourselves up to one client and wait for the connection to close. Okay, that's event-driven programming.
Imagine like this client was running, you would kind of like hack it, I guess. Could you like create a echo client that sends a message, but it's not covered in the line at the end? So then like would that make the server get stuck on the read line B?
Whatever is available on read line B, I guess you can do it for a different application. for a HTTP client. If you have a HTTP application, the client can be nasty and malicious and will not send the complete message. It can send a partial header, and the server cannot do anything until the entire header is available. For echo, it's too simple. The client, if the client sends 1 byte, the server will echo 1 byte. If the client sends 2 bytes, the server will echo 2 bytes. There is no sort of.
Does readline like, let's say the input doesn't have a UI. Would readline?
All right, so this could happen. Okay, a malicious client could, hook up a server.
Not like the normal echo client, but like maybe they were.
Right. So if you send a partial line, a malicious client could hook up the server which will not happen in a process-based server because there are separate children. Okay, that's a very good observation. So partial lines, by sending lines in a way, and these are exactly the kind of things they exploit in reality on the web. If you know the implementation of read line function, as a client, you could do things to come up with denial of service attacks and stuff like that. This is a good observation. So that's why, these standard library functions have vulnerabilities, and these are the kind of vulnerabilities that people try to exploit. If you know the implementation of a certain function, you can send a partial line here, which does not have a new line at the end, line feed at the end, and now the server is in read line, it will be stuck. This is brilliant. But I just want to say again that, because this is important for everything we'll do, when you write event-driven applications, you think of the granularity of instructions or things you want to do for each client. We don't have the echo function here. If I have the echo function here, then whenever there is some activity on a specific file descriptor, once again, the server will be hooked forever. But here we are moving on. We are scanning the list of file descriptor for events and doing something for each event. Okay, so I want to leave this. So this code is not super complicated. There's a lot of bookkeeping. You want to expand the file descriptors, ready set, read set. There are limitations. So the code is taking care of that. I'll leave it to you to come up to think of, if you just Google what is FD set size. These are all macros and constants. I don't want to go line by line, but I think you get most of the idea. So we will start with. We should have done p-threads today, but we will start with threads in the next lecture. So you have these two models, and because I don't want to, so we have some slides. I don't know what is on those slides. I just want to I don't want to start with events in the next lecture. So there is one, I think we already did that. Oh, so what the student was saying a while ago is actually how to deal with partial headers and partial lines and partial messages. This is something hard with event-driven programs. It's more complex, single thread of control, single address space. Remember that, single address space, no parallelism. There is concurrency. Multiple flows are being created by the programmer and they are executing at the same time, but there is no parallelism. It's just one sequential process. You're going over the event loop and doing something for each logical flow that you have created. The kernel is not involved in scheduling logical flows. So these are the things that you want to keep in mind. So, okay, thank you. We're done.